Good day, everyone. Let's go back and review first covalent bonding before going to our next lesson. Covalent bonding, again, it is the bonding of two or more non-metals, such as our example here, hydrogen and oxygen. So the common molecule or compound that it can create is H2O, which is the water. So if we're doing the bonding, of course, we need to follow the octet rule structure first so that we will be able to find which one is the unpaired electrons or which are the unpaired electrons and which of the atoms we have here have paired electrons, which we call also lone pairs. So for example, this hydrogen has one valence electron, that's why we have one dot. Oxygen has six valence electrons, that's why we have six dots. But look at this, there are two unpaired electrons in the oxygen, and we have also two paired electrons, the lone pairs. These are what we call as lone pairs, this group here. But in covalent bonding, the unpaired electrons are the one responsible in doing the bonding. Okay, the unpaired electrons, we will be using that later on, just to locate or to find the shape of the molecule. Okay, so for example, hydrogen and oxygen bonding with each other. So the way they do the bonding, they're gonna share their electrons to acquire the octet rule for each atom, except for hydrogen. Hydrogen only needs two valence electrons or two electrons for it to be stable. But this oxygen here, it doesn't have eight electrons yet. So of course, we're gonna add another hydrogen to make it stable. For the oxygen to be stable, we need two of the hydrogens to share their electrons to our oxygen. So our oxygen now are stable, and this is now what we call as the H2O. This will become its structural diagram. We change the shared electrons into line. So the line means we have two electrons being shared in each line. So here and here. So if you see lines in this kind of diagram, it means there are two electrons there in each line. So always keep that in mind. And the of course the one electron is owned by the hydrogen, and the other electron is owned by the oxygen, and they're sharing both of the electrons just for them to become stable. And that sharing of electrons is the reason why we have a compound. Okay, so they're holding each other because of that sharing. We call that as mutual attraction. So this is now our H2O or dihydrogen monoxide, and we call that, of course, the common word water. And this is also one of the simplest structural formula, which we don't include the lone pairs, but later on the lone pairs are very important, especially if we're trying to figure out their shape. Okay, so this is just a simpler structural formula if you want to make it much simpler. Okay, another example, to the same atom, which are nitrogens, and if we combine this nitrogen using the mutual attraction, which is applicable only for covalent bonding. So they have two lone pairs, each one of them has a lone pair, and if we combine them, they're gonna share each unpaired electron to each other. So there are three unpaired electrons for each nitrogen. So each electron, of course, they will be shared with each other. And if we rearrange the format, it will become like this. And to make it much simpler structural formula, it will be like this. Okay, there's no need for you to do this entire thing. Now if you want to do to put the dots later on, you can actually add the dots if we're proceeding to the shape of this um, molecule. But anyway, this will be a simpler structural formula. And this is now our molecule, dinitrogen, which is the nitrogen gas. And the same thing for oxygen as well, but this time the oxygen has two unpaired electrons, and the unpaired electrons are shared by the two oxygen. And we can rearrange the diagram into this and make it simpler into O with two lines for both O's. And this is now our dioxygen, which is the oxygen gas. So now um, carbon dioxide is also like this. We have carbon as having four valence electrons. Oxygen has six valence electrons, but the two unpaired electrons are the one participating in the bonding. So these two bond with each other or being shared by the two atoms. And since our carbon still has two unpaired electrons, we need to find another electrons to pair with those unpaired electrons. So we're gonna add another oxygen, and the pairing is already complete. Carbon now has eight valence electrons. One, two, three, four, five, six, seven, eight. So carbon is now stable. Oxygen also has eight. One, two, three, four, five, six, seven, eight, and the same as the other oxygen. So all of the atoms are now stable, and we call this as CO2, carbon dioxide. Okay, now the simpler structural formula is like this. If we get rid of the lone pairs, so it will be like this. So aside from looking at the bondings, the lines, we also call them as, if it is just one line, we call that a single covalent bond. And since there are two of them, so we called it single covalent bonds. And if you see two lines in like between two atoms, then we call that as two double covalent bonds. And three lines is also triple covalent bonds. Now, comparison, which one is much stronger? If ever there are some devices that we can actually break apart the atoms in a molecule, and if you're breaking them, the lowest energy is for the single covalent bond, of course, because it is single, and the strongest one that needs a higher energy is the triple bond. So it means if you want to break this nitrogen gas, or N2, it will be harder compared to the breaking of this hydrogen and oxygen here. So if you break this apart, just for you to like take away the hydrogen, it will be much easier for this part, taking away the hydrogen, compared to breaking the two nitrogens away from each other. So you need high energy to break if there are triple bonds, and you need the least energy or the lowest energy to break if it is just a single bond. And of course, double bond is in the middle, which is stronger, higher than the single bond, but lower than the triple bond. Okay? Now, aside from that, it doesn't mean if you have single bonds, it will be only seen in one compound or one molecule, just like this. There are times that in one molecule, all three of them are present, or two of them are present, just like this example. This is a molecule with single bonds, one here and one here, and with a triple bond in the middle as well. And we call this as C2H2 or dicarbon dihydride, or we call this in other word acetylene. But the question is, why is C written first aside from instead of H? Remember at the very beginning we've agreed upon no we've not agreed upon the uh, at the very beginning we talk about which one should be written first, and it says that the lowest energy electronegativity should be written first, and then after the higher electronegativity. But look at here, why is the carbon written first and then the hydrogen? Now this is IUPAC. It was established at 1919, the International Union of Pure and Applied Chemistry. So this is a global authority that they are the one in charge to create rules in naming compounds, to name the new element if ever there will be like if a new element is being discovered, then they will be the one to name that as well, and they will be the one to measure the density, everything for that element. Okay, so they are the ones giving us the rules. And one of the rule that we need to follow from IUPAC is the central atom first. And what does it mean by this? So if we're writing the chemical formula such as C2H2, this is the chemical formula. It is agreed upon the IUPAC that you need to write first the central atom before the other atoms or the other elements. So for our example here, why, although the carbon is not the center, because there are two carbons, but if we think about it, it, it is considered as the center already because both of them are carbon. So we write carbon first and then H. Okay, so that's the rule that we need to follow if ever we are writing covalent compounds. But the question is, why is H2O? We write H first and then O. Look at this. The central atom here is oxygen, but why not write it as OH2? It is because before 1919, hydrogen is the most important like element. So that is why we write H first, because at that time this is the element that is most important to them. So we follow this until now, but for the other compounds, we're gonna follow whatever the IUPAC asked us or told us to follow. Now, aside from that, according to IUPAC, the conventions that we need to follow is if ever your molecule has a carbon, carbon should always be written first. Okay? If there is a carbon in your compound, carbon should be written first. And if there is hydrogen as well, hydrogen should be written after carbon. Okay, and the rest of the elements, if ever there are elements attached to that compound, other elements aside from carbon and hydrogen, then they will be written in an alphabetical order. Most likely after hydrogen is oxygen, and that's it. Okay, so for example, C2H6O, which is ethanol. Next, C2H5Br, which is bromoethane. And the last one is ammonia, which is NH3. The question is, why? Uh, it says here in the IUPAC conventions that we need to follow alphabetical order if there are no carbon and hydrogen. There are no there is no carbon here, then we need to follow the alphabetical order. Why not write H first and then N? It's because, remember, the central atom first. Since in our structural formula here, the N is our center atom, then we're going to write nitrogen first and then the hydrogen. Okay? Now, polar and nonpolar molecules. So polar molecules, of course, we've talked about this, but I have not given you yet the things that you need to remember for each one of them, so that you will know right away which one is the polar and which one is the non-polar. Let's start with the non-polar. The non-polar is easy to remember. That's why we need to start with this one. First, it made up of one element. Okay, this is of made up of one element. H2, for example, hydrogen gas, oxygen gas, chlorine gas, and nitrogen gas. So these are molecules. Remember, we call them molecules. We call them compound if there are two atoms involved in the bonding. Since these examples, there are two atoms. Since because of this number two, it means although it is just one element, but there are two of the same element, then that is also a compound, which is we call that as a molecule. Okay, so these are nonpolar if they are just composed of one element. Now contains only carbon and hydrogen. Like for example, CH4. So this is another condition that you need to remember. Although they don't have the same, um, they don't have the same element, it is also considered as nonpolar, and I will explain later why they become nonpolar. Okay, so if there is carbon and hydrogen, they become nonpolar. Another example, C2H6, that is also nonpolar. And if they have less than 0.4 difference in electronegativity. Now, each of the element in the periodic table, they have their own electronegativity value. Okay, and the nonpolar, don't worry, you will be given the electronegativity value once you're doing like test or quizzes. There will be electronegativity value given right away in each of the elements, so it will not be hard for you to find them in the periodic table, because I think in your periodic table you don't have that written, the value of the electronegativity. But don't worry, during tests or quizzes, there will be a given table or electronegativity pair with the atom itself or the element itself. So don't worry about that. Now, in number three, less than zero point 0.4 difference in electronegativity. What does it mean by this? It means if you have two elements here, carbon and hydrogen, if you subtract their electronegativity, if the answer is if the answer is less than 0.1 4, then they are nonpolar. Just like this one, carbon has 2.55. The electronegativity of carbon is 2.55 approximately. The electronegativity of hydrogen is 2.20 approximately. So if we subtract the two, the answer is 0.35, which is less than zero point 0.4. It means this is a nonpolar. So if it is less than zero point 0.4, we can call that as nonpolar. Okay, that is another way to determine a nonpolar molecule. So if you don't know how to do this, or if the molecule is not made up of one element, then proceed to this condition. If they are uh, combination of carbon and hydrogen, then that is a nonpolar. But if the molecule doesn't, if you're not sure if this carbon and hydrogen combination is really a polar or nonpolar, check their electronegativity difference. So you just need to subtract them, the bigger number minus the smaller number, and the answer is 0.35. It means it's lesser than zero point 0.4. Then we are certain that carbon and hydrogen pair is a nonpolar. Okay, and lastly, symmetrical in shape. Hello, hello. Okay, I'm back. Okay, symmetrical. You need to follow the previous video that I gave you. So what does it mean by symmetrical in shape? For example, carbon dioxide or CO2. If we have a carbon, as since carbon is written first, it means we are now certain that carbon is our central atom. So carbon is here with 4 valence electrons, and we have oxygen. Of course, carbon is the center because it's written first. And oxygen, the two oxygens have 6 valence electrons, but we only need the unpaired electrons to pair with the valence electrons of carbon. So it will be like this. And arrange the diagram into this. So we call this linear shape. By doing this structural formula, we can now see that the entire molecule is in linear shape. And in this linear shape, although remember, if we have the if we calculate their electronegativity, like for example, carbon has lesser electronegativity compared to the oxygen. So we might think, oh, the negative is here, the positive is here, and the negative is here. Since the direction is like going that way, right? So they're pulling each other away, canceling the entire movement. Okay, so to make it polar, the arrow should not be canceled out. Like for example, if the one element is negative and the other element is positive, so the direction of the arrow should be only one direction. There should not no other arrow that can cancel this out. That's why if the shape is symmetrical, although they have difference in electronegativity, but the difference in electronegativity is being cancelled out. Okay, just like tug of war, like one of the end is being pulled away by uh, other group, and the other end is also pulled away by the other group. If they have equal amount of force, then nothing will change. So no attraction or no movement at all. Just like this, if it is symmetrical, it means the movement of the polarity will be cancelled out. We can consider this as nonpolar, although they don't have the same element. Remember, that's the one that I mentioned before. Most of the covalent bond with different elements, then we can consider that as polar molecules. But what are the few of them? And these are the few of them: the symmetrical in shape and the less than zero point 0.4 difference in electronegativity. So although they don't have the same elements in one compound, if they are less than zero point 0.4 in the difference of their electronegativity, and if they create a symmetrical shape, not just this one, not just linear, it could be a cross shape like C, and then, like, for example, H, 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 H. If they created a symmetrical shape, then that is already a nonpolar, because they're canceling out the electronegativity. Okay, I hope that's clear. Now, let's proceed. Okay, but how about water? Is water nonpolar? Okay, why water is polar? Since we've discussed that before, that water is a polar molecule. It's because of this. So let's compare the shape of hydrogen, I mean the H2O or water, and it will be like this. So what kind of shape is this? This is what we call as the bent shape. And even though they have, if we see, remember, this is our negative part, since the electrons are being pulled closer to the oxygen. Well, these are our positive part, but why is H2O considered as polar? It's because if the direction of the arrow is going this way, let's just say going that way, and also going that way. Now, nothing will be canceling out this arrow because there's no other arrow that is going opposite to this arrow. So, and this arrow is also not, this arrow will not be canceled as well by any other arrow. So the two arrows are not moving opposite to each other or going opposite direction to each other. That's why they're not canceling out, and we can consider this as a polar molecule. Okay, so H2O will be a polar molecule because of its shape, and this is what we call as asymmetrical in shape. So this is one of the things that you need to remember to determine if it is a polar molecule or not a polar molecule. So in a polar molecule, asymmetrical in shape, it means that they don't have a linear or a cross shape, or it could be like this, as long as the arrow of each line will be cancelled by the opposite line. So as long as there is like a shape like this, which we call as symmetrical. Okay, remember in your math, if we say symmetrical, it means like we can check that the opposite side is the same as the opposite side. So wherever you look, there will be an opposite side of each one of them. But if there is no opposite side of each one of them, then that is not symmetrical, and we call that asymmetrical. Okay, what are the other conditions to determine or to indicate a polar molecule? Electronegative atom is on one side of the molecule. So this is the one that we did before. Example, bromine monofluoride. So we have uh, bromine and also fluorine. If we do the bonding of the two, we have electronegativity, approximate electronegativities of the two, and the electron shared is closer to fluorine because it has a stronger electronegativity. Okay, now if we do the difference of electronegativity for polar molecules, it should be between zero point 0.4 and 1.8, between zero point 0.4 and 1.8. Okay, so if we do the difference, 2.96 for Br and 3.98 for fluorine, so if we subtract the bigger number minus the smaller number, we got 1.02. So it means this is a polar molecule because the answer is between zero point 0.4 and 1.8. So that is the third condition. Uh, First, asymmetrical. Second, electronegativity or electronegative atom is um, on one side of the molecule. And how do we know it's on one side of the molecule? Since fluorine is stronger in electronegativity, so it means this side is negative and automatically the other side is positive. And aside from that, the electronegativity difference is between zero point 0.4 and 1.8, and we got 1.02 after we subtract the electronegativities of the two elements. Then this is a polar molecule. Okay, third, last, which we call it the last one, central atom has a lone pair of electrons. And what does it mean by this? Example, any compound that has a central atom, nitrogen, which has a lone pair. Nitrogen has a lone pair. So any compound that has a central atom, nitrogen, then they are a polar molecule. If there is this one paired electron in the central atom, if you can see, if you know already the central atom, remember the central atom is the first letter that you write. If the central atom, if you do the Lewis dot structure, if the central atom has two paired electrons already from the Lewis dot structure, then you can now consider that as a polar molecule. Since in the polar molecules, the condition, the central atom must has only one pair of electrons. This should be of, not or. Okay, I was like a lone pair of electrons. Then you need to check if it is asymmetrical in shape or not. So if it is asymmetrical in shape, then even though it has two lone pairs, that is considered as polar molecule as well. Okay, so again, let me repeat the conditions that you need to remember once to indicate if it is a polar molecule or not. Electronegativity or electronegative atom is on one side of the molecule, so this is the electronegative, the partial negative, and of course the partial positive is on the other side, in the opposite side. Second, electronegativity difference is between zero point 0.4 and 1.8, just like Br and F, Br and bromine and fluorine. If we subtract their electronegativities, we got 1.02, so they are considered as polar molecule as well. Next, central atom has a lone pair of electrons. Like for example, the central atom is nitrogen and we pair this with hydrogens. So there are three hydrogens here. Then this is a polar molecule as well. if there is a lone pair that you see, then that is a polar molecules as well. So even though this is not hydrogen, as long as there's a lone pair in the central atom, then that is a polar molecule. Number 4, asymmetrical in shape. If the shape is not cross, not linear, not like this, oh wait, sorry, like this, like if there are no counterpart or opposite to each line, then that is what we call as asymmetrical. And if it is asymmetrical, then that is a polar molecule.